All right, now we're good to go. So, we're going to play off of the concept of the representative rectangle and start calculating some volumes. And I'm going to go slow with this. If I lose you, please feel free to ask. But again, the nice thing about it is it's very algorithmic, meaning you're going to do this, this, and this, and you get your answer. Okay, so it doesn't, hopefully you should be okay. All right, so we're going to find the volume of those solids. And like I talked about, those areas that we found already between two curves, we're going to take those things and we're going to spin them. We're going to spin them around the x-axis. We're going to spin them around the y-axis. We're going to spin them around some horizontal or vertical line. Now, the one thing we don't do, because it would be way ugly, would be to spin things around non-horizontal or vertical lines. It is possible, it's just really nasty, and so we don't need to bother with that. These are called solids of revolutions. They're solids that are found by revolving some area and creates a solid. And in fact, you can get a sphere by revolving a circle. And we'll talk a little bit about the calculus of that later on. So the first one is what's called the disk method. The second one is called the washer method. This will make sense when we get to it. And then today, well, maybe that's not such a good idea. Never mind. We'll just pretend that's not there. Okay. Unless it's, never mind, I didn't want to go there. Just skip that. Okay, so the disk method. Here we go. So let's talk about some terminology. I already mentioned the solid of revolution. And that is a three-dimensional figure we get by revolving some two-dimensional figures. So in this case, I'm revolving a rectangle. And when I revolve a rectangle about its axis of revolution, I get a circular cylinder, commonly referred to as a disk. And so this involves a little bit of geometry here. You'll see that this rectangle is going to be quickly replaced by our representative rectangle. So things like the width aren't going to make any sense. We're going to replace that width with a dx or a dy, depending on how it looks. And then r is the radius. And so you see, if I revolve that rectangle around that axis of revolution, it creates this disk thing. So there's a little bit of geometry there. We need to be able to find the volume of that disk. How do I find the volume of that disk? I know some of you had an outstanding geometry teacher and would remember this. Yeah, I'm looking at you. And you. And you.
Is the tire square times the wood?
Thank you, John. What excuse do you three have? Whatever. Tire squared is a circle. So think of it this way. And I don't know if you did this in geometry, but one way to process the volume of this disk is to think of it as one circle and then stack a bunch of circles on top of each other, like a roll of quarters. One circle would be pi r squared, and then W would be the number of circles that you have stacked on top of each other. So you would have a lot of circles stacked, and it gives you this volume of pi r squared times W. Also known as in the step above it, area of the disk times the width of the disk. Area of the circle times the number of circles you have stacked up on top of each other. Question?
I don't know if this makes a big difference, but does the R need to be capital?
Yes. The reason why is, that's a great question, because what we're going to do later, we're going to have two different radii, which we'll call one big R and one little r. This stuff, it doesn't matter. You can call it whatever you want. You can call it Bill if you want. But if you stay with the same method, it'll make things easier as we go through. Okay. So here's the concept of what we're going to do. If you look at this little red function there, and this is an approximation, this isn't exact. We'll talk about how to get exact in a second. But I break that area into a bunch of rectangles. And if I revolve those rectangles, I get a bunch of these disks. and then I add up all those disks. And when I'm done, I have the volume. And so what we want to do to be better, we want smaller disks or more disks. Eventually, we would like to turn something like this on the right, this big chunky disky looking thing, into that blue region, which would be an exact volume. We're looking for exact volumes, not approximate volumes. This isn't Riemann sums. This is exact volumes of these shapes. Okay. And how do we do that? Okay. So we maximize the number of disks, or we minimize the thickness of the disks. We're going to opt for number 2. Okay, so you'll see if I go back to this picture. 3, 6, 7, there's 8 disks in that range from x0 to xn. We want to increase that. How much do we want to increase it? Well, we're looking for an exact answer. So now this is calculus. We're not going to just satisfy with going from 8 to 16, or from 8 to 32, or from 8 to 100. We're going to go all the way to infinity. So if the number of disks goes to infinity, what happens to the thickness of the disks? How small?
Infinitely small.
Infinitely small, also known as? No. Good. Okay. We're going to call that dx, or dy, depending on what we're talking about. Okay? Good. So big fat rectangles isn't going to work for us. Big fat disks isn't going to work for us. We're going to keep getting them smaller and smaller and smaller until they're just a little bit bigger than 0, and we represent that value with a dx. And so you see where this representative rectangle that when we did areas didn't seem to be that relevant, seemed to be a waste of time, now becomes incredibly important in these volume calculations. Okay, so let's take a look. Hopefully this works. Yes, okay, good. Come on. Work. Ah, beautiful. Okay, so this is turned sideways, but you get the idea. So that blue little guy is my representative rectangle, which just has to be turned on its side. And if I revolve that thing, you see how it creates that disk. And what are we going to change? We're going to change the thickness of that disk, and we're going to change the line that it's revolving around. Okay?
Mr. B, I don't know if we're supposed to be seeing that blue disk, but I'm not seeing anything.
Ooh. Okay. Hold, please. Cha-ching! Now you got it?
Yeah.
Beautiful. Sorry about that. That was on me. Okay, so here's what we're going to be doing. I've got a nice, pretty little function in there. It's the square root of x. And we're going to revolve that square root of x around the x-axis from the point A to B. And you'll see that I set this to have n being 30. In other words, I'm going to use 30 different disks in order to get that revolution. So if I take one of them, I get that cute little disk. And then if you do all of them, you get that thing. And that's pretty close, but it's not where we want it to be. We want it to be the actual volume of that figure, not an approximation. So to do that, we're going to increase n to infinity, or we're going to shrink the thickness of that to 0. We'll come back to that later. Okay, so get it out of here. And now I'm going to go back to my slideshow. Okay. All right, so here we go. First example. Pictures can help quite a bit. Spend the time to draw a nice picture, and it will make the visualization a little bit easier. Okay, so here's what we're going to do. I've got some parabola, x squared plus 3. It's red in that picture. And I'm going to go from -2 to 2. You're not going to have have to visualize what these shapes look like. I just happen to have a picture of it, of what it looks like when you spin it. Okay, you get that. I want to find the volume of that green shape. The hard part is finding the volume of one disk. And once we get that, the rest is easy because we just use the calculus as an accumulator, or I should say the integral as an accumulator, to add up all those disks. So, in my picture, you can see that little blue representative rectangle. I already gave you the thickness of that rectangle to be dx because we want it to be really tiny. How tall is that rectangle? Hmm? Good. And what is R? Yes. But in this particular example, no.
X squared plus 3.
Good. Okay. So remember what we did the other day. If we're working in terms of x, if we have a vertical rectangle, everything should be in terms of x, and we're using top minus bottom. So for some of you initially, you may want to do the following. The height of that rectangle is top minus bottom, x squared plus 3 minus 0. That'll become relevant later on when we're not revolving around the x-axis. Okay? So that's the height of the rectangle. The area of that rectangle would then be its height times its width. And therefore, the volume of the disk is pi r squared times dx. So that x squared plus 3, like Cameron said, is the radius, which we plugged in, squared times pi, and the thickness of that disk is dx, because we want a really tiny disk. Question? Top minus bottom. On the top is the function, x squared plus 3. On the bottom is the line y equals 0. So x squared plus 3 minus 0, top minus bottom. Okay? Which is also the radius of that disk when it spins around. Okay? If you can get to this being the volume of the disk, the rest is easy, because now all I have to do is use an integral to accumulate all those volumes from -2 to 2. And it turns into that. Okay, so let's talk about this, a couple things about this. Number one, the first thing I always do is move the pi out in front because it's a constant and it doesn't matter. Number two, your life will be made a lot easier if you remember what it is you're trying to do. This whole business here of the x squared plus 3 quantity squared times pi is the volume of one of the disks. Oh, with the dx, I forgot to mention the dx. And then you just use the integral to accumulate all those infinite number of disks. Notation becomes very important in these problems. So for some of you that are very sloppy with your notation, you're going to have to clean it up. Things like volume equals or V equals becomes very important, because what that's telling the grader is that, yes, I know I'm calculating a volume. I'm not calculating an area. I'm not just doing an integral. I'm using this number to represent a volume. Okay, and I got that 253.841 by f anything, of course. Questions so far? Questions more so on the concept versus this actual problem. Yeah, you have a question?
So if on a test, we don't have to like solve out that integral, you just put it on a calculator.
It depends on how the problem is asked. If it's a calculator-based problem, and it doesn't specifically say show an antiderivative, then you can just go crazy with f in it. However, you will see some that are, like I said, either on a non-calculator portion, or it will specifically say show an antiderivative in order to find the answer. Okay? The reason I did this is because I don't really care about solving integrals right now. I'm dealing more with the concept. Okay, good question. Good.
Well, the width always be represented by D of X.
Yeah. Because we want that width to be really, really skinny. If we make it anything bigger than 0, all of a sudden we go back to that big clunky example of disks stacked on top of each other, which we don't want. We want that nice, smooth picture like we have there. Max?
Why does it represent dx?
Because dx is a value that implies infinitely small without being 0. So when we talk about the two possibilities to get this nice, smooth picture versus the clunky picture, we can either make the increase the number of disks to infinity, or shrink the disk down to just a little bit above 0. And so it's a lot easier to do the second one. Okay, good. Any other questions before we move on? No? Good. Doesn't seem that bad, yes? Okay, again, keep it simple. Remember what you're doing. Don't just blindly plug into formulas because it's going to get crazy. Things are going to change, and if you're just blindly plugging into a formula, you're not going to understand how to handle the change. Okay? So, now the washer method. What happens when the representative rectangle is not touching the axis of revolution? Okay. And at some point, on a sidebar here, at some point I'm going to eventually give you a nice summary chart to figure out what method you're going to use. We have a number of different methods. We have the disk method and the washer method, which we're doing today. We're also going to talk about what happens when you flip the rectangles to be horizontal versus vertical. But then we also have something called the shell method. That's for a later date. Okay. So the volume of that disk is a pretty simple calculation. It's the volume of the big disk minus the volume of the whole. Okay, and Paige, this is where we come back to your question. Notice I have two different R's here. Capital R is the largest distance from the axis of revolution to a point on the representative rectangle. Little r is the closest point from the axis of revolution to the representative rectangle. So far the question you should ask yourself is my representative rectangle perpendicular to the axis of revolution? If the answer is yes, which these all are, you're going to use either a disk or a washer. Next question, does my representative rectangle touch the axis of revolution? If the answer is yes, yes. I turned the pop on. Yeah. If the answer is yes, then you're going to use a disk. If the answer is no, you're going to use a washer. Okay. So what I did down here for the volume of the washer is I just factored it. Instead of doing pi capital R squared times W and pi little r squared times W, I factored out the pi and the W. Okay, so same concept that you're going to see in the next slide is we're going to take that W and turn it into a dx because we want a really skinny disk. Or it's real skinny washer. Okay, how are we doing so far? We're good? So this is a scenario we would use this for. And again, you're not going to have to visualize that solid of revolution, but you are going to have to be able to calculate the volume of that body. Outer radius, capital R, inner radius, little r. Outer radius, same thing as the farthest distance from the axis of revolution to the rectangle. Inner radius, little r, closest distance from the axis of revolution to the rectangle. Okay. More examples of the same thing. Okay, so there's the first one on the left is the area between two functions that we did in 7.1. On the far right in blue is what happens when you revolve one of those representative rectangles to get a washer. And then the center one is the volume that you're going to eventually find the volume, or the solid that you're going to find the volume of. Okay, so if we take this puppy we slide it off there, and then we revolve it, you see how we get a washer. So now we've talked about discs and washer just as a precursor. Eventually, not anytime soon, after spring break, we're going to calculate those, which are called shells. Okay, but that's for a later time. Let's see. We did that already. Where's the one I'm looking for? Here we go. Okay, so same idea, except I moved the axis of revolution to somewhere different, and when you revolve that, that's how we get our solid there. Okay, because again, the representative rectangle is not touching the axis of revolution. So there it is as a fancy equation. Again, move the pi out in front. And we have big R squared minus little r squared. Now, the reason I'm not a big fan of just plugging chugging into formulas is because people always screw this up. They, instead of doing capital R squared minus little r squared, they do r minus, or big R minus little r quantity squared. Whereas it should be square first, then subtract. That area should look familiar because I did that problem when we were talking about areas. And when you revolve that area, you end up getting that weird dome-looking thing. So we're going to take a 10-minute break. In that 10-minute break, I would like you to try to set up, and if you're feeling saucy, F a hint, the answer to this problem. I would like to know the volume of that blue shape. Okay, so I'll give you some hints to get you started. My representative rectangle is perpendicular to the axis of revolution. Therefore, I'm going to use a disk or a washer. My representative rectangle is not touching the axis of revolution. Therefore, I'm going to end up with a washer. Okay, the rest is on you. Set that up, find the volume. All right, let's take a look at this problem, and I'm going to set it up, but I'm going to do a lot more work than need be, just so that you can appreciate the where these things come from. So a common thing happened in this classroom that I'm sure that happened in the classroom that may have happened to you at home. A lot of people got 0.3 as an answer, whereas the actual answer was 0.924. We'll talk about that in a second. But We already went through the fact of why I know this is going to be a washer. So the volume of this puppy then is going to be pi times the integral. I'm taking rectangles from 0 to 1. So that sets up my limits of integration. I'm going to do this. I know that I have to do capital R squared minus little r squared times dx. Okay. So how do I get capital R? In the picture, you're already given that value, but I'm going to take it a step further, and I'm going to say this distance of capital R is still top minus bottom. The top is the square root of x. The bottom is minus 0. So I would do square root of x minus 0 quantity squared. Now that's ridiculous. Why would I do that? I wouldn't. But I want to show you the thought process because it is going to become relevant in a little bit. Minus little r. Well, little r is over here. Again, top minus bottom. The top of that is x squared. The bottom is 0, so it would be x squared minus 0 quantity squared. And I don't know what just happened. And those have a thickness of dx. And again, that dx is relevant to the problem. Now, walking around here, I realized that people didn't do that. They didn't put a minus 0 in there because that's silly. If you get this down to the volume equals pi times the integral from 0 to 1 of the square root of x quantity squared minus x squared quantity squared dx. Fantastic. If you want to simplify that before you fn int it, that's fine. X minus x to the fourth, or you could just plug that monster in as fn int. The common mistake that happened here is people got 0.3 because they forgot that little pi sitting out in front. Okay, so your answer has to be multiplied by pi, which gave us 0.92. 0.42, okay. So there's all the setup, boom, boom. I think I have an answer there somewhere. 3 pi over 10, whatever that is, I don't know. There's the exact answer. But I'm guessing that most of you fn inted it. Same thing, okay. All right, so again, addressing Yanni's question earlier, well, when do we have to go through all this business versus when can I just fn int it and get to the decimal equivalent? It depends on the problem. Again, the problem will tell you very specifically. You must show an antiderivative to get full credit. Well, in that case, you need to go through the antiderivative process, which was this. If it doesn't say, then just fn int the crap out of it. Pretty good stuff.
Yeah, why is there a minus 0 there?
Because it's top minus bottom. The top of this distance is the function, square root of x. The bottom is the axis of revolution, which is 0.
Oh.
Always coming back top minus bottom, top minus bottom, top minus bottom.
Will there be instances where it's top minus 0?
What you can't see right now is I have a big grin on my face underneath my mask. It's coming. Yeah, it's going to be fun. You'll be okay. Won't kill you, hopefully. So, there's our question. What if it's not the x-axis or the y-axis? This is where the top minus bottom becomes relevant. Okay. So here's my picture. I think we did something like this similar, or before I should say. I've got a couple functions here. I've got, let's color code this. This is the red function. This is the blue function. But I'm going to revolve it around the line y equals 3, which isn't in the picture, so I'll draw it in. Here is my axis of revolution. Okay. And we're going to go slow. And you're going to hear me repeat myself over and over again. But hopefully, eventually, by repetition, it will burn into your brain. So the first question I ask myself, is my representative rectangle perpendicular to the axis of revolution? Yes. Therefore, I have a disk or a washer. And initially, the answer to that first question is always going to be yes, because we haven't talked about the other one yet. Is my representative rectangle touching the axis of revolution, yes or no? By the way, the green is my representative rectangle.
No.
No, it's not. And since it's not, that means I'm going to use the washer. So what I've established is that this is going to be a washer. Why isn't my pen working? Getting angry. There we go. All right, washer. Which means I need a big R and I need a little r. And this problem complicates things for a couple of reasons. Number one, we're revolving around a non-axis. And number two, I put the axis above everything else. So for those of you that are visual learners, this distance is capital R. It's the farthest distance from my representative rectangle from the axis of revolution. This little distance is little r, the closest point from the axis of revolution to the representative rectangle. Okay? All right, so the volume is going to be equal to, we're taking rectangles from 0 to 1. How do I know that? Well, it says x equals 0, x equals 1. How big is capital R?
Is it 2?
No, it's not 2. It is 3 minus the quantity, 1/2 x plus 1. Paige, you're going to need to explain that.
Well, you said it's top minus.
Loud.
It's top minus bottom, so the top is the line y equals 3, and then the bottom would be the y equals half x plus 1.
Good. Okay, before I move on, any questions about where that came from? Keeping it simple, top minus bottom, as she said. Okay, now in order to get to that, you have to be able to recognize the capital R in the function itself, which is that farthest distance. Okay, so this is capital R squared. Okay, minus. What's little r?
3 minus square root.
Beautiful. 3 minus parentheses, x squared plus 2. Parentheses, very important. Quantity squared. Let me get that line out of there. This is a mess. There we go. And then don't forget that pesky little dx, because that is the thickness of all of our disks. This back end is little r squared, which is exactly what we're looking for. Now, that's not something you want to solve by hand. You don't want to have to multiply that out. You could. I would simplify this out first and get 2 minus 1/2 x quantity squared and 1 minus x squared quantity squared. Multiply it all out, combine like terms, do all that fun stuff, or just slap it into fn in. Because again, solving this right now is not my concern. It's being able to get it set up. That should be the actual challenge here. Okay, go ahead, fn in that. Tell me what you get. Especially since it's good practice to plug that in to make sure you're plugging it into your calculator correctly, using your parentheses correctly. Don't be bashful when you get an answer, shout it out. We'll see if other people have the same answer. We'll do majority rules. Max?
8.01.
Say it again.
8.01.
8.01. Anybody got a confirmation? Same thing. And did you multiply by 5 just to be sure? Beautiful. We'll go with it. Wow, that's a mess. Hold on. Get rid of all this. There it is. Okay. There we go, that's better. Okay, top minus bottom for radius, top minus bottom for little radius, and we are done. I don't know why that says, hey, you know what? I think we're going to keep going here. Because, oh, by the way, does anybody get the joke?
Yeah.
You all know what that is, right? Okay. You don't know what that is? That's what's called a floppy disk. That's how computer stuff used to be stored. 3.5-inch floppy disk. Good times. And that's a washing machine. Didn't know, I mean, you know, kids these days, I don't know if you ever use that thing or you just rely on the P's to do all your laundry, but that is a front-loading washing machine. So we got discs and washers. Okay? Yeah.
Do you like the front-loading washer or the top-loading washer?
I've always had a top-loading washer because I'm a little freaked out by the idea that the front door opens and it just blasts water all over the lawn. I'm sure it never happens, but you can't do it.
I mean, I guess it could happen. Anything's possible.
Yeah.
Yeah. I've had both, and I also prefer the top.
Top-loading, yeah. Okay. All right. So, shall we? We shall. Okay. Now, I wanted to cover this last little bit because then I can say I just did all this for you, and then we'll do some damage control on Thursday, and then pick up where we left off when we come back from spring break. But this is going to address the idea of what happens when our rectangles are horizontal. So remember when we talked about an area. If the rectangles are horizontal, everything has to be in terms of y, and we're doing right minus left. Okay, I believe I have a graph here somewhere. I do not. I thought I had a graph with this. Okay. So I have this function y equals x to the fifth, and I want to take rectangles from y equals 1 to y equals 32. So graph that on your calculator so that you can see what that looks like. Graph x to the fifth, and then set your window from like 0 up to 35 for the y value. Okay, so before I go through all of this, because I don't have a picture, I'm going to sketch a picture of what's going on here. So I've got this function that looks something like this. And I want to take rectangles from 1 up to 32, and I'm going to revolve around the y-axis. So one way to show your axis of revolution is to draw a little arrow around it so we know which way we're revolving. Now, if we stayed with a horizontal rectangle, you can see what kind of problem that would cause, because I'm no longer perpendicular to the axis of revolution. So in this case, I would like to use a horizontal representative rectangle. And I'm going to draw it over here. Okay, there's my rectangle. I know that its thickness, I'll put that in right away, is dy. That's the easy part. The same question that I asked earlier would still apply here. Is my representative rectangle perpendicular to the axis of revolution? Yes. Is it touching the axis of revolution? Yes. Therefore, I have a disk. I think the disks are easier to use. All I have to do is find the volume of one disk and integrate. So my volume would be pi times the integral of, I'm going from 1 to 32, because I'm taking these rectangles from 1 all the way up to 32, because that's what the problem says. And now I need the width of that rectangle, which is also our radius. The problem is my function is in terms of x. Therefore, I can do a quick calculation here, and that's a 5. X is equal to the 5th root of y. Because again, if my rectangles are horizontal, everything needs to be in terms of y. Here's my radius. And so, since my rectangles are horizontal, I'm going to do right minus left. The 5th root of y minus 0, quantity squared, dx. And again, do we really need the minus 0? No, but since we're learning, I want to put that in there so that you continue to see this right minus left, top minus bottom. Because my rectangle is horizontal, and once it's horizontal, everything has to be in terms, whoops. Everything has to be in terms of y. There we go. Screwed up. Okay, go ahead. Tell me what the answer is. Remember, when you're doing fn int with a value of y, just put in x's instead of y's, you'll get the same answer.
164.934.
Okay? Anybody else? Other way?
I think
You didn't get that. What'd you get?
284.
284.
Or 284. Oh, I'm correct.
So common mistakes we've already seen. Number 1, forgetting to multiply by pi at the end. Forgetting to square your radii or radius, depending on the problem. Cameron, question.
Do we have to put a unit? Is it like?
We don't. It's not crucial at this stage.
Should that be?
If you're feeling saucy, you can throw a unit squared on there.
Okay.
You know, unit cube. But it's not really what I. At this stage, we don't care.
Okay.
284.987.
Yeah.
Okay, so this is just a summary of the things I already talked about. Right. And the things that we did with area carry over into here. If it's in terms of x, then if your rectangles are vertical, everything's in terms of x, and you're doing top minus bottom. If your rectangle is horizontal, then you're in terms of y, and everything is right minus left. And the breakdown is, are you perpendicular to the axis of revolution? For now, the answer will be yes. Is it touching? Yes, then that's a disk. No, then it's a washer. Okay? Last example, which I'm going to go through quickly, which I think should be fairly obvious. But notice, just like the other things we've talked about, when calculating the volume of this figure, the top and the bottom change, or the right and the left change. Be clever about this. What do I mean by that? What I mean by that is you're all fairly bright. Notice from this point downward is just a cylinder. You don't need to use calculus to find the volume of a cylinder. Just do some geometry. You need calculus for this stuff up above. That's geo. That's calculus. Can you use calculus for the bottom? Sure. Knock yourself out. But I would argue that most people will probably find that easier just to do pi r squared times the height, which is 1. Okay, and then use calculus for this. This is also an example of a problem that you could use vertical rectangles for if you wanted to, because the function is fairly easy to use. Okay. So that big thing, I included the calculus here, but we don't need this because that's just geometry. I probably wouldn't do that. This you're going to need because that's the volume of the top part of that dome-looking thing, or that cup-looking thing. Okay. And then all the work, blah, 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 blah. Who cares? Excellent, great. We're done. All right, I know that this was a very long lesson.